In the past few videos, we've been talking about the normal distribution. Now we're going to move on and talk about a different kind of probability distribution, the binomial distribution. Binomial distributions allow us to model the probability of a certain number of successes in a given number of trials. So to motivate this discussion and to talk a little bit more about what these concepts mean, let's go ahead and begin with an example. In this example, let's stipulate that the probability among Ohioans of supporting the Browns in the NFL is 35%. And now let's say that we take a random sample of 4 Ohioans to ask them about their favorite team in the NFL. What's the probability that exactly one of these 4 Ohioans is going to support the Browns? So we're going to go ahead and name these people in our sample. We're going to call them Alan, Brittany, Caroline, and Damien, or A, B, C, and D for short. And we're going to go ahead and look at the condition of exactly one of them supporting the Browns. One way for this to happen is if Alan is the subject that supports the Browns and the other 3 do not. Scenario 2 is a situation where Brittany supports the Browns and the other 3 do not. In scenario 3, Caroline supports the Browns, and in scenario 4, Damien supports the Browns. In each of these scenarios, the probability of exactly one of those people, or that particular person supporting the Browns and the other 3 people not supporting the Browns, is 0.0961. That's the 0.35 probability of one person supporting the Browns, multiplied by the probabilities for each of the other 3 people not supporting the Browns. So 0.35 times 0.65 times 0.65 times 0.65 equal to 0.0961. If we add all 4 of these probabilities together, we end up with the overall probability of exactly one of 4 people supporting the Browns. So that ends up being 0.3844. That's 0.0961 multiplied by 4 for each of those 4 scenarios. So let's go ahead and add some mathematical notation to this. A given number of successes is denoted with the letter K, and the given number of trials is denoted with the letter N. So in this example, we were just talking about one success in 4 trials, so K equals 1 and N equals 4. And we calculated this probability by multiplying the number of scenarios, that's each of the 4 scenarios in which one person supported the Browns and the other 3 did not, times the probability of an individual scenario. So let's go ahead and talk about the components of this calculation in a little bit more detail. I'm going to talk about the number of scenarios in just a minute. How do we decide how many scenarios are possible with a particular number of the outcome that we're looking for? And then the formula for the probability of a single scenario happening is the probability of success raised to the power of the number of successes times the probability of failure raised to the power of the number of failures. So we just did this by multiplying 0.35 one time times 0.65 3 times. So P is 0.35, K is 1 success, so 0.35 raised to the power of 1. 1 minus P is 0.65, and we multiply by that 3 times, which is N minus K, 0.65 to the power of 3. So we're going to continue going over how we calculate binomial probabilities, but let's stop for a minute and talk about the formal definition of a binomial distribution. The binomial distribution describes the probability of having exactly k successes in n trials with a certain probability of success, which we denote p. The parameters of the binomial distribution, the things that define the shape of the binomial distribution and the probabilities within that distribution, are n and p. So recall that the parameters of the normal distribution were the mean and the standard deviation. In a binomial distribution, the parameters that we're looking at are the number of independent trials and the probability of the conditions of success in any individual trial. In a binomial distribution, we want to know all of the possible scenarios in which the condition that we're looking for could occur. So in the example that we were just looking at, the condition we were looking for was exactly one person out of 4 people surveyed saying that they supported the Browns. So we found out that the number of scenarios in which that could happen was 4. There were 4 possible ways in which only one of those 4 people supported the Browns. In other binomial distributions, where the number of trials that we're interested in and the number of successes that we're interested in are different, especially when they're higher, this gets a lot more complicated. So for example, let's say that we wanted to survey 9 people about whether they supported the Browns, and we wanted to know the probability that out of 9 people, exactly 2 would support the Browns. So there are a lot of different scenarios in which this could happen. And I've graphically represented some of them here. We could have, for instance, persons 1 and 2 supporting the Browns and nobody else, persons 2 and 3 supporting the Browns but nobody else, persons 3 and 4 supporting the Browns but nobody else, persons 3 and 6 supporting the Browns and nobody else, persons 8 and 9 supporting the Browns but nobody else, and lots of other possible permutations in between. So this would be really difficult to get wrong, and it would be really tedious to list out all of the possible ways that exactly 2 of 9 people could support the Browns. So, luckily, we have a mathematical shortcut to make our lives easier when we calculate the number of scenarios in which a particular condition can happen. The function that we can use to calculate the possible number of scenarios is called the choose function. We say this as n choose k, and it's calculated as n factorial divided by k factorial times n minus k factorial. A factorial takes the given number and then multiplies it by that number minus 1 times that number minus 2 times that number minus 3 all the way down to 1. So for example, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So if we want to know the number of scenarios when we have n equal to 4 and k equal to 1, that's 4 choose 1, which is equal to 4 factorial over 1 factorial times 4 minus 1 factorial, which is equal to 4 times 3 times 2 times 1 divided by 1 times 3 times 2 times 1, which is equal to 4. When k is equal to 2 and n is equal to 9, we want to calculate 9 choose 2. So out of 9 trials, choose 2 successes. That's 9 factorial divided by 2 factorial times 9 minus 2 factorial, which is equal to 36. So on the previous slide, when we were talking about all of the different permutations for the scenario in which we surveyed 9 people and wanted to know how many times 2 of them could support the Browns, there were 36 total possible scenarios in which that could happen. You can calculate choose functions manually. You can also use the calculator built into R by using the function choose n, comma, k. So when n is equal to 9 and k is equal to 2, as in our second example here, we'd say choose parenthesis 9, comma 2, close parenthesis, and we would get the answer 36. So to calculate binomial probabilities, we need both of these components of the equation, the number of possible scenarios and the probability within a given scenario. So to calculate the probability of k successes and n trials, we're going to use this formula. Keep in mind, p means the probability of success, 1 minus p is the probability of failure, n is the number of trials, and k is the number of successes. So the probability of getting k successes in n trials is n choose k multiplied by p to the power of k times 1 minus p to the power n minus k. So that's a little complicated and maybe not very intuitive, so let's put it to use by doing an example. In this example, we're looking at a 2012 Gallup survey that found that 26.2% of Americans are obese. If we took a random sample of 10 Americans, what is the probability that exactly 8 of those 10 would be obese? First, let's test some intuition. Take a minute and think about whether given this probability of obesity, is there a pretty high probability or a pretty low probability that if we took a sample of 10 people, that 8 of them would be obese? So your intuition should be that this probability is pretty low. There's less than a 30% chance of obesity. So if there were 80% of our sample that was obese, that would be quite surprising. Let's work this out in a little bit more detail. What is N in this example? What is K in this example? And what is P in this example? So we're interested in how many trials, how many successes, and what is the probability of success. So you should be able to figure out that N is equal to 10. We're taking a sample of 10 Americans, so 10 trials. K is the number of successes that we're interested in, the outcome that we're interested in, which is obesity. So K is equal to 8. And the probability of the outcome, the probability of success, is 0.262. So let's use the formula that we looked at on the previous slide to find the probability that K is equal to 8 in this distribution. That probability formula is N choose K times P to the K times 1 minus P to the N minus K. So just take those numbers and plug them into this formula that we have. And we find that the probability K is 8 is equal to 10 choose 8 times P to the 8th, so 0.262 to the 8th, times 1 minus P to the N minus K, so 0.738 to 2, which comes out to be 45 times 0.262 to the 8 times 0.738 to the second power, which is equal to 0.0005, or 1/20th of 1%. So under these conditions, there's a really, really small probability that if you took a random sample of 10 Americans, that 8 of those 10 would be obese. Let's continue probing this example. I want to ask, if you took a random sample of 100 Americans, how many would you expect to be obese within that sample? Well, if 26.2% of the population is obese, our best guess is that 26.2% of a sample will also be obese. So 26.2% of a sample of 100 people is 26.2. More formally, what this means in a binomial distribution is that the mean of the distribution is equal to N times P. So the number of trials times the probability of success in a given trial. 100 times 0.262 is equal to 26.2. So this doesn't mean that any time we take a random sample of 100 people, we're going to find exactly 26.2 people to be obese, because of course that's not possible. In some samples, we're going to find that fewer people are obese. In some samples, we're going to find that more people are obese. But how much would we expect this value to vary? So the proof for finding out what the standard deviation of a binomial distribution is not really important for this class, so I'm just going to give you the formula here. We expect that the standard deviation is equal to the square root of N times P times 1 minus P. So the square root of the number of trials times the probability of success times the probability of failure. So in the example that we were just talking about, N is equal to 100, P is equal to 0.262, and 1 minus P is equal to 0.738. So if we multiply those three quantities together and take the square root, we find a standard deviation of about 4.4. So we already found that the mean of the distribution that we were just looking at is 26.2. So we would expect that on average 26.2 of the people in our 100-person sample would be obese. But let's also think about what the range of outcomes that we would think of as usual or ordinary, what that range of outcomes would be. So we've already explored a little bit the notion that observations more than 2 standard deviations away from the mean are considered unusual. So let's look at the range of 2 standard deviations below the mean to 2 standard deviations above the mean as sort of a good range of usual outcomes that we would expect if we took a sample of 100 people from the population. So we're going to take the mean plus or minus 2 standard deviations. So 26.2 plus or minus 2 times 4.4. That's plus or minus 8.8. That gives us a range of 17.4 people to 35 people that we would not be surprised to see as the number of obese people in a random sample of 100 Americans. So let's do one more example to explore these concepts. An August 2012 Gallup poll found that about 13% of Americans think that homeschooling provides an excellent education for children. So if we took a random sample of 1,000 Americans and found 100 people shared that opinion, that homeschooling provided an excellent education, would that be unusual, or is that an ordinary number of Americans who hold that view in a random sample of 1,000? This would be a great opportunity for you to pause the video and work this out using the formulas that we've already discussed. So if 13% of the population thinks that homeschooling provides an excellent education, and we take a sample of 1,000, we're going to get a mean of n times p, that's 1,000 times 0.13, which is equal to 130 people. That's our best guess for how many of the people in our sample are going to have this view about homeschooling. Our standard deviation formula is the square root of n times p times 1 minus p. We have all of those quantities. N is 1,000. The probability of holding this view about homeschooling is 0.13. The inverse of that probability is 0.87. So if we take the square root of 1,000 times 0.13 times 0.87, we get about 10.6 as a standard deviation. If our range of usual observations is the mean plus or minus 2 standard deviations, that's going to give us a range of 130 plus or minus 2 times 10.6, or a range of 108.8 to 151.2. So this is sort of the range of observations we would not be surprised to find in a random sample of 1,000 people. 100 is lower than the lower bound of this range. So if we found that in our sample 100 people only had this view about homeschooling, that would be unusual. If you recall from our discussion of z-scores, we said that a z-score higher than 2 or lower than -2 is something that we would consider unusual for an observation. So we could also answer this question about the Gallup poll by calculating the z-score of the observation 100. So we would take z equal to the observation minus the mean divided by the standard deviation. So 100 is the observation, our mean, our expected mean is 130, and our standard deviation we just found is 10.6. If we solve this out, we find a z-score of -2.83. And recall, because a z-score outside of the bounds of -2 and 2 is unusual, this is more illustration that finding 100 Americans in this sample of 1,000 would be unusual. So that's some basic information about the purpose and the parameters of the binomial distribution and how we use binomial distributions to answer some basic research questions. For the last part of this lecture, we're going to do a little bit of synthesis. We've talked about the normal distribution and about the binomial distribution. Now we're going to talk about something called the normal approximation to the binomial distribution. So to motivate this, first let's go ahead and look at these hollow histograms of different binomial models with different parameters. In each of these models, the parameter p is equal to 0.1, but the number of trials is changing from 10 to 30 to 100 to 300. So how does the shape of these distributions change as n increases? Well, what's happening is that these distributions are starting to look more and more normal. So, as n is increasing, the binomial distribution is starting to resemble the normal distribution more and more. So how can we use this knowledge? How can we go back and forth between looking at the binomial distribution and the normal distribution? How big does n have to be for us to be able to think of the binomial distribution as approximating the normal distribution? Our rule of thumb is that the expected number of successes should be greater than or equal to 10, and the expected number of failures should be greater than or equal to 10. So n times p and n times 1 minus p should both be greater than or equal to 10 for the sample size to be considered large enough to use the normal approximation. So here are a couple different sets of binomial parameters. For which of these could we use the normal distribution to approximate the binomial distribution? So in which of these cases is np greater than 10 and n1 minus p greater than 10? You'll find that only in case B do these conditions hold. In case A, n times 1 minus p is only 5. In case C, n times 1 minus p, n times p is only 7.5. In case D, n times p is only 7.5. But in case B, np is 11.25 and n1 minus p is 13.75. So in that case, even though n is the smallest out of all of these examples, because of the value of p, this is the case in which the normal distribution would be an okay approximation for the binomial. So we've established that when the sample size is large enough, we can approximate the binomial distribution with a normal distribution. But normal distributions come in lots of different shapes and sizes, literally. So how do we know which normal distribution is appropriate to use as an approximation for the binomial? What are the parameters of the normal distribution that we need? Here are the formulas that we need to go from our binomial distribution parameters to the relevant normal distribution parameters. The mean should be np, and the standard deviation should be np times 1 minus p. So you find the mean and the standard deviation of your binomial distribution, and you use those as the parameters for the normal distribution. So if we had a binomial distribution where n is equal to 245 and the probability of success is 0.25, the mean of that distribution, the mean of the normal approximation, should be 245 times 0.25, which is 61.25. And the standard deviation should be np times 1 minus p, the square root of that, which is 6.78. So the binomial distribution with parameters 245 and 0.25 can be approximated by the normal distribution with parameters 61.25 and 6.78. And here's how that looks. This is a histogram of the binomial distribution with those parameters overlaid with a normal distribution with the correct parameters for a normal approximation to that binomial distribution. And that brings us to the end of this lecture on the binomial distribution. Thanks for hanging with me, and I will see you next week.